Let's get started. So last time we were talking about how to, if you're interconnecting a policy, and I copied the definition of policy on the board with an MDP, and we have the definition of MDPs on the board too. You interconnect them, they induce a stochastic process or a distribution over some sample space such that there are these random variables S0, E0, R1, S1, and then A1, R2, S2, AT, R, T plus 1, ST plus 1, which are defined over omega, and there is a probability distribution over omega, which is really a function of three things. Keep forgetting that. There is an initial distribution as well, mu. So the MDP, and we suppress the dependence on the MDP, and then there is the initial distribution, mu, and there is the policy, pi. And I was arguing that there is a powerful mathematical theorem that says that this distribution exists so that you can continue this sequence of random variables indefinitely such that some meaningful consistency conditions hold, which I was giving for prefixes of these random variables, like what's the distribution over the prefixes of these random variables up to time t, and arguing that you could continue this indefinitely, which we want to do because we want to talk about the return on an infinite horizon. So the return, if you start at time t, is just, and we're talking about discounted returns, then you go with an increment of 1, and you take the rewards for the corresponding time steps, you're discounting them. This gamma is a discount factor, and this is the return, and this depends obviously on infinitely many random variables. And eventually we want to take the expectation with respect to this distribution P, so this distribution better exists before we write those things. All right, but we know that these exist. That was Kolmogorov's theorem. I add some links sometime soon, where you can look up what this theorem says. It's called Kolmogorov's extension theorem, if you're curious. It's called an extension theorem because you are specifying a probability distribution over prefixes, and you want to claim that you can extend this indefinitely. That's why it's called extension theorem.
Should the index be s plus t plus 1? Because
oh, yeah, absolutely. It's, yeah, t plus s1 plus 1, or yeah, any order of t and s. Good catch. Yeah, please do that. If I write something that shouldn't be there, or like you see some inconsistency, you better stop me. Okay. So this P exists, this distribution P. sometimes, very often, we use some properties of this distribution P, which is not the definition, but follows from the definition. So what are these properties? There are 3 of these properties that are important properties. So if you want, this is a proposition. So if P is constructed the way it was on the board last time, then for that P is going to hold, the following is going to hold. First of all, it's kind of obvious. If you take the distribution, the marginal distribution of this P just with respect to the first state, S naught, then this marginal distribution has to be mu. So the probability that the first state, which is confusingly the 0 state, but like, okay, fine, S naught is little s naught, should be equal to mu of S naught, and this has to hold for every possible state. So the initial distribution is really doing what it is supposed to do. So that's a property just for the initial distribution. And the way to remember that we need 3 properties is because we had 3 objects that determine P. They were the initial distribution, and then what's the next? The transition. Okay, so the next is going to be the transition probabilities, P, little p. And then the very last one, the policy. Okay, so that's going to be policy pi. So for each of them, we're going to have some properties. So with regards to the transition probabilities, we want to claim that the Markov property is going to hold. That was the whole point of everything that we were doing before, in a way. So for every t greater than equal to 0, it has to hold that if you look at the distribution over a pair of rewards for the next time step and next state. So there is also a for all for the whole history up to time step t, which was like S naught, A naught, R1, S1 up to RT, ST. Okay. Suppose there. And also whatever AT is going to be. So this is in the history space. Okay, don't be messy. Why do they make these boards so small? AT is an action, and ST plus 1 is a state. And I don't know whether that thing is going to record if I write that far. Oh, it does. Awesome. I can go all the way to the end. And RT plus 1 is a possible reward. So this probability, okay, so the policy is going to come here. Don't forget that. The conditional probability of seeing this reward in next state, given that the history, and so the history is up to here, all of these guys, I call them HT. Okay, so that's the history up to time step t. The history equals to HT. And the action is equal to AT, is equal to big climax, little p. What should I write here? Someone was saying something?
Maybe the same thing, but except now you have the history is not.
Okay, but just tell me like what letter comes here.
I don't know.
Little r, t plus 1. What comes here? R, st, at. Good, we're done. So, also known as the Markov property holds for the so-constructed stochastic process. No wonder. This is what we wanted. But we had the definition for P. And if you have a definition, you make a claim, you better be able to prove that those things do hold. I'm going to leave this to you. I can't prove everything in class, but you're welcome to do it. Maybe it's going to be, I don't know, question, an exam, I don't know. Who knows? We're going to do similar things. Okay, so that's the Markov property. And then finally, we want to make some connection to the policy and capital P. So for that, it's going to be very similar to this, except that I would just need to say that somehow this capital P is related to the policy. Well, what does the policy do? It selects actions. So it's like the conditional probability of the action chosen to be whatever it is given the history should be equal to the probability assigned to the action by the policy, right? So no surprises. So the probability, according to this capital P, of assigning the probability, some probability to some action given some history should be equal to T, AT, given the history. And this has to hold, again, should come first for all t greater than or equal to 0, all little ht in ht, and little at in A. So that I religiously write little at and like this index is t, index is t, and whatnot. It helps me to, keep track of things. But of course, you could replace this with numbers if you have numbers in those states, or other letters. It doesn't matter, right? So it's just a convention that asks me to think about these things. So there is this proposition. And interestingly, so the proposition says that P satisfies 1, 2, 3. There is a converse of this. If you have any P that satisfies this, then it would satisfy the property that was on the board the last time, that the prefix probabilities are equal to the products of this and this and this and this. So you can reverse this statement. So the reverse also holds. So proposition reverse also holds. Every P such that 1 to 3 holds will be such that, and okay, like I better write it. For every t, the probability, and I just write it with the history because it's kind of the same. Oh my God. So much writing. Yeah, you might think that like, oh, this is a lot of writing, and you're right. So the history abruptly ends at st. Okay, so we have rt and st. That's the last thing. So you write out all these products, they alternate. So there is a policy here coming P1, A1, given, blah, 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 history, and so on and so forth. So they alternate. these terms. Yes.
Sorry. So for the third point, so you're saying that it is denoted as like the policy 5 of AT conditional on H3, but are the policy maps the actions over the distribution of states, correct? So, but H3 depends on
No. No. A policy takes histories, looks at what happened before, and we want to remember, an action to the system. So it has to come up with a distribution over the actions. So that's what it does. And you said it assigns probabilities to states, it assigns probabilities to actions, given a history. Okay.
The random variable H3 depends on the reward, the previous actions, and everything. That's kind of why I was confused.
Yeah.
The policy.
Right. Yeah. Like policies can depend on the full history.
I see.
They can. Yeah.
Okay.
So this is what we were discussing the last time, that we want to have at the end, we want to be able to say, but that policies don't need to depend on all of these things if you only consider whether you have an optimal policy or not. Then policies don't need to do that. But in order to be able to discuss that, first we're discussing the case when policies would depend. And that's the general case. Anyway, all right. Good? All right. So there was one more thing the last time. And this was new. Yes. Someone? Right. No. Okay. I just misheard my name. Okay, so the last time we were also starting to talk about value functions and their definitions, right? Okay, so what was that? We have the return, and from the return, that's random because it depends on the random rewards, which depend on everything. From the returns, we want to get some non-random things. So we want to take expectation. And the return is going to depend on whichever state you are starting your policy with. Okay, so which one? Well, we're going to consider all of it, right? Like for all possible initial states, what is the expected value for the return? So we collect this into a function, and we're going to call that the value function of the policy. And we just need to formally define this now. And then the understanding is going to be, at the end, you want a policy which maximizes this value function regardless of the initial state. And then we want to argue that you can do that. It's kind of a multi-objective optimization again. Like this keeps coming back, multi-objective optimization. It's kind of weird. Because you want to simultaneously attain the maximum possible value across all states. And it's kind of like a small miracle that you can do that, and you can do that even with a policy that doesn't need to remember the past. So it's not usual that for a multi-objective optimization problem, you have this single best solution that simultaneously maximizes or optimizes all the objectives. It's a very nice structure that we have here. And of course, the whole thing was set up in such a way that this should happen, but it's still, it's kind of like we have to realize it's not the usual case. Okay. So this has begun. Let's write the definition for value functions. So to write the definition of a value function, I was arguing that the best thing to do for us to have the cleanest definition and clean definition is if we choose an initial distribution which restricts the initial state to a specific state. Let's say you have S. So you want to start from here. Then you choose the initial distribution that puts a probability mass of 1 on this state, which you can do So you choose mu s prime at some other state to be 0 if s prime is not s, and otherwise if s prime is s, then you choose it to be 1. And for this, you probably already got used to this, that I use a lot this indicator function. It's the single most useful invention in mathematics. I don't know, I just love it. It turns everything into algebra and saves you all these cases and whatnot. So the indicator function has this argument, and it's a predicate. And if the predicate is true, then it returns a 1. Otherwise, it returns a 0. OK? So these two things are really just the same. And the indicator function is just a much shorter way of writing the same thing. And it's super, super useful. So one of the nice properties for indicator functions is that somehow, if you have probabilities and expectations, it very nicely connects the two. Actually, you can define expectations only starting from indicators and then build everything up from the indicators. That's people do that. So indicators are super beautiful and useful. Okay, so anyway, so we have this mu, and I want to give it a name because it's like a special mu. And so the last time I was using mu s to denote this particular initial distribution that puts a probability mass of 1. And another name of it could be that it's just like a delta function, a Dirac function. It puts the probability mass on somewhere where it is putting the probability mass is in the index as well. So if like that's another notation, and normally I would use that notation. So maybe from this point on, I would just use this notation. OK? And then you take any policy pi. It can be history dependent, can have memory. And you define the value that pi generates starting from s as the expectation under the initial distribution that you chose and the policy pi of the return. OK, which is just G0. Simple enough. So we didn't have much discussion about why we choose expectations. I mean, you have this random quantity. The expectation terms a random quantity which is very rich. It's like this return. Random quantity, it has a distribution, right? And you just like take that and then summarize it with a single number. It's expectation. It's expected value. And OK, why expected value? Well, there are other choices. This is not the only choice. And depending on the situation, maybe you would want to use something as. So you better know that like this is not the only choice that people study. The expectation is beautiful because it's linear, it's simple. It's also kind of like first approximation. It's like the first thing that you may want to know about something that's random. It's expected value because, I don't know, if you want to gamble with your friend, then that's like the average payoff that you would get in the long run. And so if you need to pay for that gamble, then this is kind of the certainty equivalence value for a gamble, so that if you pay this amount, then you're not losing anything. And so if you pay more, then you're going to lose. If you pay less, then you're going to win in the long run. And so it's kind of like, you know, this kind of thinking. So we're going to stick to this because we don't have time to cover everything. But there is beautiful math beyond expected values as well. OK. So this looks pretty impenetrable. It looks kind of complicated notation. By the way, this E delta S pi, so that's the expectation that is induced by the corresponding distribution. So if I have a distribution, that is an expectation operator that corresponds to that distribution. If I change the distribution, expected values do change, right? Like you can have the same random variable, but suddenly, you know, everything looks different because distributions are different. So that's a notion. Okay, so G naught. It was this infinite sum. Okay, if you have an infinite sum, first comes to mind, does this even exist? Is this even well-defined? So can you give me an example where this would not be well-defined? A sequence of RTs, yes? For example, yeah, but maybe tell me also what RT would be in that case, a simple example. Right. Yeah. Right, correct. So for example, if you choose gamma to be greater than 1, and RT is just constant, this is an exploding sum. Then the sum doesn't exist. So then what are we talking about? We want to talk about things that do exist. So if gamma is less than 1, and between 0, so it's not like -5, that would also be problematic. Its gamma is, you know, like it gives you the present value of money given this, like how much in the future you're going to get that much money. That's kind of the thinking, maybe. But maybe it's just like a nice mathematical trick. But OK, so gamma is between 0 and 1, strictly less than 1. Then give me an example where this sum still doesn't exist. Wait. Maybe? OK. Give me just an example of sequence of rewards where we run into trouble. Like 1, 2, 3, 4, and so forth. Yeah, exactly. So then this is not summable either. Does it have to be like that, that it's increasing the reward for us to get into trouble? So let's investigate a case when edge case gamma is equal to 1. And some weird examples. I mean, like, of course, in that case, if you have the constant example, we are already in trouble. Constant 1, 1, 1, 1, that just runs away. But what if, like, we had 1 and then -1, and then 1 and then -1, and then 1 and then -1? Is that summable? Right. I mean, like, for these things to be well-defined, it has to make sense. So summing up 1, -1, 1, -1, it depends on where you stop, where you end. It never converges. That's not summable. So in mathematical terms, you want this absolute summability condition. So in absolute values, if the sum exists, then we're good. So that's OK. What does this mean for us? We have this Markov decision process. We made some decisions at the beginning, which may help us at this moment. So what were those decisions? Like, how is our MDP very, very special here? I didn't say that at the beginning of this class, but we discussed this a while back. Are we considering, you know, any big state space, any, you know, big cardinalities?
All the actions.
I mean, that's maybe still too big. I think, yeah. No, no, not really that. There is a restriction on how big these sets, S, A, and P, are going to be. And yes, it was true that at one point we were talking about discrete and not discrete, and discrete is at most countable. But we even dialed back, even further dialed back on that.
We
We
want them finite.
want them finite. Yeah, exactly. So we are discussing finite MDPs. And that is going to save us here. How? Yeah. And explain why. Well, we have the rewards there. So maybe we want to argue about the rewards. So what do we do? Yeah, the possible values the rewards can take on is also finite. So the maximum value that the reward can take on in absolute value must be a finite value. Can be big, but it's a finite value. And then you can, sum the absolute values of the rewards, because the largest absolute value that you can get is maybe 5, comes out of the sum. The remaining is a geometric series. It sums to 1 over 1 minus gamma. So that upper bounds the return. So that everything is finite. Well, we only use that. I mean, we are kind of lucky that everything is finite, that the rewards in absolute value are bounded with a specific value. So more generally, if you have bigger MDPs, finiteness would not be needed if you have an MDP such that the same property holds. That with, if you're generating a random reward from your transition kernel, with probability 1, you see that it's bounded by an absolute number, a fixed constant, you would be still good. Then the return is still well-defined. So we're kind of lucky here. Good, well-defined. So since this is well-defined, its expectation is also well-defined. But it's not, you can't take this for granted. So if you had an infinite MDP, let's say the state space is infinite. And as maybe the states are numbered from 1 to infinity. And as the index of the state increases, maybe the reward increases. Maybe it increases faster than gamma to the power of t decreases. And then we would be in trouble again. So you can be in trouble in many ways. And actually, that's not a completely outrageous example. So in robotics, for example, people would consider, spaces like, what's the velocity of the arm of my robot? And okay, like you will never see infinite velocities, but if you're getting really large velocities, usually your system breaks. So that's not good. So you want to penalize that. So you would have negative rewards, which are increasing as the velocities are increasing. So you're kind of in that situation. And then it's not even obvious whether a discounted sum like this is going to exist. It depends on how fast the state is going to increase, how fast you're pumping energy into your system so that the velocity is exploding. So that's called the lack of stability. In robotics, a lot of the things are about, okay, I want to keep everyone safe. My robot should also be safe. I want to keep everything bounded. But it's not taken for granted that it's bounded, because you can have these runaway positive feedback loops. You flip a sign by accident, and then rather than decreasing the velocities in the right moment, you're increasing them, and then you have a runaway process. You don't want to be around when that happens on a real robot. Especially, okay, so there are the toy robots, and then it's fine. It's just like, anyways. So some of the big robots are in cages because of this, by the way. Like, kind of funny that, like, we have to be separated from the human. Okay. All right, so no issues with infinities. Good. So the next discussion is that writing this random rewards and then taking expectation, all of that, the book introduces this notion of immediate reward as well. So there is this 2-argument reward function. So little r is mapping states and actions to the reals. And the idea is that, well, that's the expected reward that you expect to see if the system was at state S and you took action A. What would be the immediate reward? What would be the expectation of the immediate reward that you see in the next step? Okay? So the definition of this is that this is just the expectation with respect to this transition kernel P. So that's like, we have to write, okay, I do have a lot of choices to make. So let's say I write it this way. So an expectation with respect to something is like value times probability. So this could be a definition. That's a meaningful definition of the expected reward that you're going to see. And if you read books, I wrote a book. In that book, I don't bother that much with this thing. So I immediately flip, instead of using this random reward, to use the expected reward for that time step. So I write things like V pi s should be defined as the expectation with respect to this distribution. Initial state is s, policy chosen is pi, and then I don't sum the random rewards, but I sum rather the expected immediate rewards. Okay, since our definition is this, so this is our definition. This must be a proposition. So this is either true or not. You think it's true? Well, obviously, since many people write it, must be true. Someone would have discovered if this was not true. Yeah, okay, so this is kind of funny that you kind of just like took away this, and then instead of the RT plus 1, you have this R, ST, AT. Can we prove this?
Because we're using the definition, I guess, then you want to swap sums or something. If you use the definition of RSA, but I guess then you want, I guess everything is bounded, so you can't swap sums that it's valid mathematically. But then, yeah, I need to write it down.
Okay, let's start to write. Like, okay, you got some ideas, so let's try to write a proof for this. After all, sometimes you gotta write some proofs. This eraser is not working that well. Kind of leaving some black taint. All right, proof. Okay, so we have the definition. So let's start from the definition. You can't do much. You have the definition. And the only thing I can do is that, okay, we wrote G0 there, but like that's T opaque. So let's write out the definition of G0. So that's just this. Okay. And then I guess, what was your name?
Robert.
Huh?
Robert.
Robert. Okay, that should be easy to remember. Robert. So the idea was that maybe we can swap the sum of the expectation, right? Yeah. So what do we know about that? So if you have a random variable x and another one y, this is always equal to this. Yes, 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 everyone. Is there anyone who objects? No objections? I do object. Object? Good. Wait, so we're just talking about the below relationship. So there is no infinite sum here, just two variables. We're summing them up. Then it's okay. I mean, I'd better have both of these expectations defined. At the left-hand side, we should know it's defined, or we should know that the right-hand side is defined. So what is a case when an expectation is not even defined? What does that even mean? The expected value of something is not defined. There is such a thing. I mean, like, right? So I cannot claim that, like, these are supposed to be values. They have to be values for me to be able to claim that they are equal. So either at least these two guys should be defined, or at least this guy should be defined, because it might happen that none of it is defined, and then what are we talking about? It's kind of like a weird case, but it's good to keep in mind. So what is a case when the expectation of x is not even defined? What is that? What's x? What's the probability with respect to it? Like, how do we do anything like that? Okay, we have to go back and remember how was expectation defined. Let's say everything is discrete, right? Because here everything was discrete.
Sum of x times the probability of getting that right.
Right. So normally, like, okay, x is discrete. Then you say that, okay, x can take on some values, and you list all the possible values, and it should be countable, because that's when you have discreteness. And there is a probability assigned to that x takes on that value, and times x. That's usually the definition. What the heck is this sum? What is that doing? How many terms do we have there?
Like, it depends on your speed, whichever it comes.
Right. So for genera, for discrete random variables, it could be finite or infinite. If it's finite, yeah, everything is defined. If it's infinite, and we have an infinite sum, we just discussed that infinite sums are problematic, right? You can have plus minus one, plus minus one, plus minus. You can run into all kind of troubles. So when is an infinite sum defined? How do we say that it's defined? And the order in which we are summing here, it's not even specified. So if we want to write anything like this, then we have to think about this, that like this has to exist. So how do we make sure that it exists? Yeah, like we had this term that earlier came up, absolutely convergent series, right? So you want absolute convergence. All right, so a little detour.
You would have like even point or the uniform, any, or is it like absolutely one you want for?
I think in this case, nothing else works, especially if you're using this, because this notation, this means that the ordering shouldn't matter. So if the ordering shouldn't matter, then it is going to be either absolute convergent or it just doesn't make sense. Yeah, so in this case, it's like, really, this is nailed down to absolute convergence. So that in absolute values, if you're putting, so this series is going to be absolute convergent. If you order this, this is an enumerable sequence. So you can get any ordering of it, like x1, x2, and xn, arbitrary ordering. And if in that ordering, the following series, okay, let's say I'm numbering them from 1, that the probability that x is equals to xi, so that's one of these probabilities, times in absolute value, x of I. This is a well-defined series. So that means it converges, which we usually denote just by saying that it's less than equal to plus infinity. Then we're good. OK. So this is the condition. OK. So backtracking here. So you can construct examples, but these things are not well defined. And therefore, there is no sense of talking about that these two guys are equal. So whenever you're swapping expectations and sums, you always have to think about, are the individual expectations well defined? OK. If you can claim that the individual expectations are well defined, you're OK. Or if you can also claim that somehow magically you figure out that this expectation on the other side is well defined, again, you're going to be fine. So that's the theorem that tells you that you can swap expectations and sums. The linearity of expectation holds as long as things are well defined. All right, good. Back to our case. And like, OK, challenge problem, you think about some case. You heard about a lot of cases when series do not converge, whatnot. Maybe you can figure out a case when this would not make sense because things are not well defined. Anyways, back here. So we want to move this sum outside of the expectation. We have an infinite sum on the top of it. How do we do that? We could try to do it one by one, and then use induction. It's kind of the lame tool, but kind of works if you have just countably infinite things, right? So one idea is to break this into a finite sum. Maybe it's sum of two terms. So which term should I break off? So if I write this out, there is an infinite sequence of terms, or infinitely many terms. Which one do I break off? I could take out any of them, but I mean, I'm going to keep things simple. Yeah, we'll just take the first. So which one is that? That's R1. And then you have the same thing. Right. And so now, OK, that's challenging. So now we would need to argue that the expectation of either of this is well defined, or the expectation of just this, and the expectation of this is well defined. That seems to be a chicken and egg problem to me, actually, right? Because this sum pretty much looks like as the previous sum. We didn't do much. We just broke up one term. There are still infinitely many terms in there. So that doesn't work. OK, are we stuck? No. We have our friends, past mathematicians, not personal acquaintances, but nevertheless friends that help us. There is this guy called Lebesgue. He came up with some very cool tools. So he came up with many things, but all right. One of the things he said is that if you want, so you can think about this sum here. So it didn't work that we were trying to break off one term and then all the rest. So we can try to go the other way. Take the prefix. Oof. All right. So call that a function, or that's a random variable, new random variable. And then basically what you want is that we know that Fn converges to this limit of infinite sum, because that's like absolute convergence. That's just the definition. That's what we were talking about before. And what you want is that if you have a sequence of these random variables and it converges pointwise to something, then you want to know whether the expectation also converges of these random variables. All right. And just give me literally a minute. If you have some other function or another random variable that upper bounds the absolute value of f, and the expectation of g exists, so that's a well-defined quantity, then Lebesgue tells us you can do this. All right. So our CMPUT didn't work. We had to call Lebesgue. It's all good. So we can use this theorem to argue that you can swap the expectation with the infinite sum under the condition you find this g. So what is this g? I think it was on the board at one point. Basically, you take the absolute values here. You call this g tilde 0. This is going to be the g. So now you have to argue that the expectation of this is well-defined. But what you can do is that you can just upper bound this by the maximum possible value divided by 1 over 1 minus gamma, or divided by 1 minus gamma. That's an upper bound. So that's an upper bound on an expectation. So the expectation is well-defined, and all is fine. We can swap expectations and infinite sums. All right. So see you on Friday. Getting there.